Friends, imagine a colossal object, 6 miles wide, hurtling through the infinite expanse of space at 12 miles per second, headed straight for Earth. It's crucial to emphasize that this isn't a figment of science fiction. 66 million years ago, such an asteroid collided with what is now the Yucatan Peninsula, leaving behind the gigantic Chicxulub crater and triggering a mass extinction event. Today, our planet remains under potential threat from so-called near-Earth objects, NEOs. This category includes asteroids and comets whose orbital paths intersect with our cosmic neighborhood. NASA and other space agencies have made significant strides in tracking and deeply understanding these potential threats. Yet the risk of a fatal collision still persists. Advanced technological solutions are actively employed for continuous monitoring and effective mitigation of these threats. Humanity is developing diverse strategies to protect our world from these cosmic intruders, ranging from kinetic impacts to gravitational tractors. However, a natural question arises. What would happen if an asteroid comparable in size to the one that formed the Chicxulub crater were once again on a collision course with Earth? How truly prepared are we for such a catastrophic event in the modern world? The study of planetary defense, its historical development, scientific foundations, and future prospects becomes critically important in light of such serious threats. So, 66 million years ago, an event of such catastrophic proportions occurred on our planet that it fundamentally altered the entire course of life's evolution on Earth. An asteroid, approximately 6 miles in diameter, slammed into the Yucatan Peninsula, located in modern-day Mexico, creating what we now call the Chicxulub crater. The immediate aftermath of this collision can only be described as apocalyptic. The impact released a colossal amount of energy, equivalent to billions of nuclear bombs exploding, leading to widespread wildfires and powerful tsunamis, and ejecting enormous quantities of debris into the atmosphere. The most significant and long-lasting effect of this impact was the injection of dust, soot, and sulfur aerosols into the atmosphere. These tiny particles formed a global cloud that blocked sunlight for an extended period, a phenomenon often referred to as impact winter. Recent research has shed light on the crucial role of fine dust particles in this grand cataclysm. A study published in the prestigious scientific journal Nature Geoscience in October 2023 demonstrated that fine dust, particularly particles with diameters ranging from 0.8 to 8 micrometers, played a significant role in the abrupt and dramatic climate change. Scientists collected 66 million-year-old rock samples from North Dakota, a considerable distance from the impact site, and found an astonishingly large amount of these fine dust particles. These particles remained in the atmosphere, forming a dense cloud that persisted for up to 20 years, with the first 5 to 8 years being the harshest. This prolonged period of darkness led to a significant drop in global temperatures, estimated to be more than 18 degrees Fahrenheit in the first year alone. With sunlight blocked, photosynthesis ceased entirely, and plants, deprived of their ability to produce food, began to die en masse. This collapse of plant life triggered a cascading effect throughout the entire food chain. Herbivorous dinosaurs, whose existence directly depended on plants, faced mass starvation. Consequently, the carnivorous dinosaurs that preyed on them also perished. This chain reaction led to the extinction of approximately 75% of all species on Earth. Notably, the new study highlights the previously underestimated impact of dust compared to soot and sulfur, which were previously considered the primary culprits for the prolonged cooling period. The findings indicate that while soot and sulfur are more effective at blocking sunlight, the colossal quantity and remarkable persistence of dust had a profound and long-term effect on the climate. The research also provides valuable insights into how some species managed to survive this dark period. Plants and animals that hibernated possessed adaptations that allowed them to endure the prolonged absence of sunlight. However, the study questions certain survival mechanisms of freshwater organisms, indicating that further research is needed to fully understand the specific mechanisms of mortality after the Chicxulub impact. So, what exactly are near-Earth objects? They are asteroids, comets, and other celestial bodies whose orbits bring them close to Earth. These objects vary in size from small, completely harmless rocks to massive bodies capable of causing widespread and destructive catastrophes. Asteroids are rocky remnants from the early stages of our solar system's formation. Most of them are concentrated in the asteroid belt, located between the orbits of Mars and Jupiter. Comets, unlike asteroids, originate from the distant outer regions of our star system and are composed of frozen ice. To minimize these risks, leading space agencies, such as the National Aeronautics and Space Administration, NASA, and the European Space Agency, ESA, have developed and implemented comprehensive programs for continuous tracking and detection of near-Earth objects. Telescopes located across the globe tirelessly scan the celestial vault, identifying and cataloging objects that approach our planet's orbit. One of the key instruments in this vital work is the Wide Field Infrared Survey Explorer (WISE) telescope, which was specifically repurposed for the NEO-WISE mission. It has discovered and characterized hundreds of near-Earth asteroids, significantly expanding our knowledge of them. The role of artificial intelligence in detecting previously unobserved asteroids is becoming increasingly significant. In May 2024, an AI-powered algorithm known as Trackless Heliocentric Orbit Recovery, or THOR, identified over 27,000 previously unnoticed asteroids in archival telescope images. This innovative AI tool analyzes colossal volumes of data, identifying and tracking celestial bodies with astonishing efficiency. It can process up to 1.7 billion light points in a single telescope image, linking them into complete asteroid trajectories. The Vera C. Rubin Observatory, scheduled for launch next year, will further enhance our capabilities for detecting near-Earth objects. Equipped with advanced AI software, such as HelioLink 3D, this observatory is expected to catalog millions of asteroids in its first few months of operation, doubling the current known population of these celestial bodies. Nevertheless, it is important to note that no single near-Earth object is large enough to completely destroy Earth itself. However, asteroids 1 mile or more in size are indeed capable of causing global catastrophes. For this reason, NASA is tasked with detecting and tracking these large NEOs. As of 2021, NASA has discovered over 90% of the largest objects, ensuring that none of them pose an immediate threat to Earth. However, smaller objects, while not as catastrophic on a global scale, can still cause significant regional damage. Take, for example, Apophis, named after the Egyptian god of chaos and destruction. This near-Earth asteroid has attracted considerable attention from scientists and the public. Discovered in 2004, this 1,000-foot-wide asteroid initially caused serious concern, as preliminary calculations suggested a possible collision with Earth in 2029. However, further, more precise observations ruled out this possibility, confirming that Apophis will safely pass our planet. On April 13, 2029, Apophis will make an incredibly close approach to Earth, within 30,000 miles of our planet. For perspective, this distance is closer than the orbits of some high-altitude satellites. Such a close approach provides a unique and unprecedented opportunity for scientific observations and research. During its flyby, the asteroid will become visible to the naked eye in some regions of Earth, appearing as a bright, moving point of light. This rare event will allow scientists to study its size, shape, and composition with unprecedented detail. NASA's Deep Space Communications Complex in Goldstone, California, will play a crucial role in observing Apophis with radar. Scientists hope to gather detailed information about the asteroid's surface features and rotation. Additionally, the NEO-WISE mission may provide further observations, focusing on Apophis's surface roughness and chemical composition. These data are invaluable, as they will help refine our understanding of near-Earth asteroids. NASA's OSIRIS-APEX spacecraft, formerly known as OSIRIS-REx, is preparing for a close encounter with asteroid Apophis during its closest flyby. The primary objective of this mission is to study the celestial body in detail from close proximity, providing unique observations unavailable to ground-based telescopes. OSIRIS-APEX will collect data on the chemical composition and structural features of Apophis's surface, as well as record any changes that may occur to the asteroid as it approaches Earth. The instruments aboard the spacecraft will help determine the asteroid's internal structure, which in turn will significantly contribute to expanding our overall understanding of the formation and subsequent evolution of the solar system. The upcoming close flyby of Apophis has also attracted keen interest from international space agencies. Scientific teams from around the globe are actively planning activities to observe and study the asteroid, using both ground-based and space-based telescopes. As part of the NEO-LID project, researchers from Julius Maximilian University of Würzburg have presented several concepts for small spacecraft that could accompany Apophis during its flyby. One proposed mission involves sending a small satellite to follow Apophis for 2 months, collecting high-resolution images and measurement data. Another concept suggests integrating a small satellite with the European Space Agency's planned Ramses mission, allowing for extensive scientific observations. Although the asteroid currently poses no direct threat to our planet, its close approach in 2029 provides an exceptional scientific opportunity. Intensive study of this celestial body at close range will significantly advance our planetary defense strategies. To ensure Earth's safety, scientists have developed a range of planetary defense mechanisms, each designed to prevent potential collisions. One key method is the kinetic impact strategy. This approach involves sending a spacecraft to collide with an asteroid at very high speed, thereby altering its trajectory. The essence of the method is to transfer momentum to nudge the asteroid into a safer orbit. NASA's 2022 mission, the Double Asteroid Redirection Test, or DART, was the first practical test of this method. DART's target was a small moonlet of Didymos, named Dimorphos, which orbited the larger asteroid Didymos. The collision successfully altered Dimorphos's orbit, providing invaluable data for developing future missions. Another proposed method is the gravitational tractor. This technique uses the gravitational pull of a spacecraft to gradually alter an asteroid's trajectory over time. By maintaining a stable position near the asteroid, the spacecraft's gravity can slowly but surely change the object's path. While this method remains theoretical and has not yet been tested in space, it represents a promising approach for countering potential threats detected early on. In extreme cases, however, nuclear explosions may be used to deflect or even destroy an asteroid. In this approach, a nuclear device is detonated at a safe distance from the asteroid, vaporizing part of its surface and creating a recoil effect that pushes the asteroid off its original course. Nevertheless, this method raises serious controversy due to the potential risks and legal implications associated with using nuclear weapons in space. To comprehensively prepare for potential asteroid impacts, international space agencies regularly conduct simulations and exercises. These activities help practice strategies for detecting, tracking, and deflecting hazardous objects. Planetary defense is a global issue requiring close cooperation and coordination among various countries. For example, in 2021, NASA participated in an international planetary defense exercise organized by the International Asteroid Warning Network and the UN Office for Outer Space Affairs. The exercise simulated the detection of a fictional asteroid on a collision course with Earth, allowing participants to practice their response strategies in near-real conditions. As humanity continues to develop and refine its planetary defense strategies, international cooperation and technological advancements will play a crucial role in safeguarding our world from any cosmic threats. These collaborative efforts are absolutely essential, especially as we gain more knowledge about the diverse nature of objects that potentially threaten us. Asteroids and comets, these amazing celestial wanderers, are traditionally perceived as completely distinct classes of space objects. Asteroids, by their very nature, are rocky fragments remaining from the time our solar system formed. Their main concentration is found in the so-called asteroid belt, located between the orbits of Mars and Jupiter. Comets, in contrast to asteroids, are mysterious visitors from the most distant corners of our star system and consist predominantly of ice, cosmic dust, and inclusions of rocky material. Nevertheless, in the boundless expanses of space, unique specimens are encountered that, by their nature, blur the clear boundaries between these two categories, simultaneously exhibiting characteristics of both asteroids and comets. One such extraordinary object is 2005 Q173, discovered by astronomers in 2005. This truly unique celestial body orbits in a manner characteristic of an asteroid, yet it exhibits activity typical of a comet. Unlike the vast majority of ordinary asteroids, which remain inert and show no activity, 2005 Q173 displays noticeable cometary activity. As it approaches the Sun, it ejects dust particles, forming a long, thin tail behind it. Space object 2005 Q173 completes a full orbit around the Sun every 5 years, spending most of this time in the outer region of the asteroid belt. However, as it approaches the central star, it demonstrates sharply increasing activity, resembling the behavior of a comet. This astonishing duality makes 2005 Q173 a subject of close study and immense interest for astronomers worldwide. In the summer of 2021, a group of astronomers using the Asteroid Terrestrial Impact Last Alert System, ATLAS, in Hawaii, detected an object exhibiting a characteristic cometary tail. Subsequent observations by the Lick Observatory and the Zwicky Transient Facility convincingly confirmed this activity. The tail, reaching a length of 450,000 miles, strongly indicates that the object's surface is covered with icy material that sublimates when heated by sunlight. It is this process, where ice directly transitions to a gaseous state, that releases dust and creates the characteristic cometary tail. Notably, the extraordinary narrowness of the tail indicates that dust particles barely leave the nucleus, moving at extremely low velocities. This fact presents a genuine enigma for scientists, as such small velocities typically do not allow dust to overcome the asteroid's gravitational pull. One hypothesis suggests that the rapid rotation of the celestial body's nucleus may contribute to dust ejection. In addition to unique objects like 2005 Q173, many other near-Earth objects pose a potential threat to our planet. The European Space Agency maintains a detailed and comprehensive risk list, which catalogs objects with a non-zero probability of colliding with Earth. This list contains detailed information about each object's size, speed, and collision probability. It currently includes over 1,600 potential targets. The risk list is sorted according to the Palermo scale, which is a logarithmic scale designed to assess collision risk based on a combination of parameters such as object size, speed, and collision probability. Objects with higher Palermo scale values represent a greater potential threat. Statistical analysis of these potentially hazardous asteroids clearly shows that while most near-Earth objects pose minimal risk, there are several objects that require the closest monitoring. For example, an asteroid's size and speed have an extremely significant impact on its probability of colliding with Earth and the potential damage it could cause. Large asteroids, typically exceeding 1 kilometer in diameter, are of particular concern due to their ability to cause global catastrophes. Fortunately, NASA and other space agencies have identified and tracked over 90% of these large objects, ensuring that none of them pose an immediate threat to Earth at present. Smaller objects, while not capable of causing such catastrophic consequences, can still inflict significant regional damage. Events such as the Chelyabinsk meteor impact in 2013 and the Tunguska event in 1908 vividly demonstrate the potential danger posed by small asteroids. As humanity continues to discover and track near-Earth objects and to refine our planetary defense strategies, international cooperation and technological advancements remain critically important. By understanding the diverse nature of these celestial bodies and preparing for potential threats, we can protect our planet and ensure a safer future for generations to come. Every few years, the seemingly tranquil Pacific Ocean hides something beneath its surface that stirs its depths. A powerful force is born there, a climatic phenomenon that radically changes weather patterns across the planet. Its name is El Niño. From torrential rains causing catastrophic floods in South America to severe droughts leading to massive wildfires in Australia, El Niño is not just a localized tropical anomaly. It is a global disruptor of climate patterns. But what causes this mighty climatic phenomenon? Let's try to understand. El Niño, whose name in Spanish means the boy, has a significant impact on the world's ocean environment, causing it to warm approximately 32.4 to 32.9 degrees Fahrenheit above average temperatures. This natural phenomenon was first recorded in the 16th century. It manifests in all corners of our planet, and its consequences can include floods, droughts, an increase in atmospheric carbon dioxide levels, and global changes in temperature regimes. The spread of El Niño begins in the eastern part of the central Pacific Ocean, as a result of which developing countries located along the shores of this ocean, as well as marine organisms unable to quickly adapt to abrupt climate changes, suffer most from the sudden rise in water temperature. However, El Niño is not the only phenomenon capable of influencing global weather conditions. In essence, El Niño represents only one phase of a larger climatic phenomenon called the El Niño Southern Oscillation. This cycle can exist in two other states. One is La Niña, which is the complete opposite of El Niño, and the other is a neutral state, when no significant impact from either of these phases is observed. La Niña, which in Spanish means the girl, is a weather phenomenon that causes cooling rather than warming of water masses. In general, water temperatures during La Niña decrease by as much as 37 to 41 degrees Fahrenheit. The consequences of this phenomenon for many countries around the world, such as the United States and Canada, include heavy rains, floods, and more intense hurricane seasons. But the most difficult part is that these two phenomena are extremely hard to predict, which in turn makes preparation for them difficult. They occur every 2 to 7 years, so they are not regular. Moreover, they are not short-term events. El Niño lasts about 9 to 12 months, while La Niña typically lasts from 1 to 3 years. El Niño and La Niña do not appear out of nowhere. Their formation is a very unusual and complex process. Under normal conditions in the Pacific Ocean, trade winds move from an area of high atmospheric pressure to an area of low pressure, moving from east to west. These wind currents carry warm water along their path, closer to Asian countries and Australia. Thus, cold water masses rise in the east off the coast of South America, which also beneficially affects fish catches due to the enrichment of such water with nutrients. This process is called upwelling. Warm water in turn heats the air, causing it to rise rapidly into the lower atmosphere and then condense, while colder air returns to the eastern regions, thereby maintaining the strength of the trade winds. However, if this delicate balance is disrupted in any way, El Niño or La Niña begins to develop. During El Niño, the winds significantly weaken, as a result of which warm water is less affected by their movement, and the intensity of upwelling also decreases. Consequently, the water column in the Pacific Ocean begins to warm evenly, even in areas that usually remain cold. This in turn leads to changes in precipitation patterns, causing dramatic weather transformations in all corners of the globe. For example, in tropical latitudes, the probability of floods significantly increases, while in Western countries, arid periods intensify. As a striking example, consider the Pu'uwa'awa'a protected area in Hawaii. Under normal conditions, the average rainfall there is about 2.7 inches in January, but under El Niño conditions in 2010, only 0.4 inches fell. However, over time, one El Niño event can transform into another, for example, into La Niña. During La Niña, winds, on the contrary, significantly strengthen, leading to increased upwelling and a decrease in areas occupied by warm water in the ocean. For example, the western regions of the United States and the northern parts of South America may experience a noticeable cooling, while areas of the Indian Ocean, on the contrary, may face warming. Consequently, regions directly bordering the Pacific Ocean suffer most from these climatic phenomena. Approximately 30 to 60 million people died due to severe droughts and floods in India, China, and Brazil in the 19th century. In the 20th century, 26 El Niño events were recorded, which had a serious negative impact on crop yields in Western countries, as well as on populations of various animal species, including sea lions. Thus, the main victims of El Niño are South American countries such as Peru and Ecuador. A significant part of these countries' economies depends on the export of fish and fertilizers. However, due to El Niño, upwelling decreases, leading to mass fish mortality, and precipitation increases, as a result of which crops and fertilizers are washed away, and civil infrastructure receives significant damage. Meanwhile, eastern regions such as Indonesia and Australia face the threat of droughts. These natural phenomena lead to the drying up of water bodies and agricultural lands, which negatively affects the well-being and health of both people and animals, as well as soil fertility. East African countries, for example, Kenya or Tanzania, as well as countries on the American continent, suffer from abundant rainfall, while South Central countries, such as Zambia or Mozambique, experience the consequences of an arid climate. The southern states of the United States, especially Texas, also experience an increase in precipitation during El Niño periods. However, for example, in California, this atmospheric phenomenon, on the contrary, brings rains, which favorably affects the yield of such agricultural crops as lime and avocado. It is noteworthy that Canadian winters become milder during these periods. Curiously, El Niño also affects Antarctica. Its western part experiences a slight warming, contributing to increased snowfall, but at the same time, a decrease in upwelling leads to the melting of ice shelves. Conversely, La Niña contributes to the growth of these glaciers, thereby helping to maintain the natural balance. The direct impact of the El Niño phenomenon on European countries is quite difficult to document. Nevertheless, El Niño brings cold and dry winters to the European continent, which can be detrimental to agricultural lands. For example, in the 18th century, El Niño had a significant impact on crop yields in European countries, which was likely one of the reasons that triggered the start of the French Revolution in 1789. Already in the 19th century, this atmospheric phenomenon caused about 3 serious famines in various Asian and European states. Thus, El Niño and La Niña represent very dangerous climatic phenomena for our planet. El Niño and La Niña were last recorded in 2015 and 2016, almost 7 years ago. 2016 was recognized as the hottest year in meteorological history. It was the most powerful of all previous El Niño episodes in the last 50 years, leading to famine for more than 60 million people. In 2015, equatorial waters remained warmer than usual throughout the calendar year. The central part of the ocean then warmed by almost 37.4 degrees Fahrenheit at its peak in November, and the total warming temperature reached 35 degrees Fahrenheit, which is likely a record value since 1860. All continents felt the impact of El Niño, whether direct or indirect. For example, Australia experienced severe droughts, especially in its eastern and northern regions. This led to an early start to the fire season on the continent, with a total of 125 fires. The fire caused serious damage to vast natural areas in Tasmania, including rainforests and wetlands that had previously almost never burned. Moreover, during this period, the most massive coral bleaching was recorded, a process that causes them to whiten and makes them extremely vulnerable to death. Spring and autumn of 2016 in Australia were among the driest in meteorological history, which significantly affected crops. In addition, the heat reduced the supply of ore, the country's most exported commodity. Regions of Asia also suffered from various weather anomalies. For example, 85% of the territories of the Philippines and Indonesia experienced severe drought. In Indonesia, large-scale fires broke out, which significantly worsened air quality in adjacent areas, including Singapore, Malaysia, Thailand, and others. The fires also affected palm oil exports, leading to a rise in prices for this product and, consequently, for all food products in which it is used. In addition, rice production in Vietnam and Thailand significantly decreased, in particular due to a lack of water resources. India, in turn, reduced supplies of rice, sugar, cotton, and corn. The northern regions of China suffered from droughts, while the southern regions were affected by rains and floods. South America suffered greatly from weather disasters in all its regions. In 2016, Peru experienced powerful floods and landslides, as a result of which about 5,000 people lost their homes and shrimp production decreased. Moreover, 150,000 people were forced to evacuate from flooded areas in Paraguay, Brazil, Argentina, and other countries. In addition, Argentina faced one of the largest locust invasions, which seriously worsened the state of agriculture in the country. Add to this the return of heavy rains in April 2016 in Colombia. Due to droughts, famine began, and about 2.3 million people needed humanitarian aid, according to the United Nations. In the Caribbean, there was an acute shortage of drinking water, and St. Lucia even declared a state of emergency in the country. The varying impact of El Niño in Brazil led to a sharp increase in global coffee and sugar prices. The United States and European countries, in contrast to the aforementioned regions, practically did not experience the direct impact of the El Niño phenomenon. Individual states such as Missouri and Mississippi, as well as the United Kingdom, recorded an increase in precipitation above annual averages, but this did not entail significant economic consequences for their national economies. And finally, the African continent also suffered significant economic damage from this climatic phenomenon. Thus, in South Africa, food production decreased by 6 million tons. In some areas of Zimbabwe, a significant part of the harvest, reaching 75%, was lost. 10 million people in Ethiopia were in urgent need of humanitarian support, and approximately 458,000 children were being treated for acute malnutrition. In total, 60 million people worldwide suffered from hunger. Among other things, adverse weather conditions provoked outbreaks of various diseases, especially noticeable in Africa and South America. For example, as a result of large-scale floods in several South American countries, the Zika virus began to spread actively. In Africa, outbreaks of cholera and Rift Valley fever were recorded in the eastern regions of the continent, as well as malaria. In particular, representatives of the animal world also suffered from the consequences of El Niño. This concerned seabirds and small mammals, which sometimes forced predators to attack livestock. Populations of invasive species such as locusts and tree frogs also showed significant growth, harming agricultural crops and contributing to the spread of dangerous infections. The seriousness of the threats posed by the El Niño and La Niña climate phenomena should not be underestimated. Meteorological services are already recording precursors of El Niño, which is highly likely to begin in late summer 2023 or very early 2024. According to Dylan Amaya, a researcher at the National Oceanic and Atmospheric Administration, NOAA, and Petteri Talas, Secretary General of the World Meteorological Organization, there is a risk of new global temperature records being set next year. One reason for such pronounced intensity was the unusually long La Niña phenomenon, which lasted 3 years and ended only in March. Thus, a significant amount of thermal energy accumulated in the ocean waters, and therefore, after the cooling period, all this heat will be released, which will inevitably amplify the effects of El Niño. At present, it is difficult to say with certainty whether the 2015-2016 scenario will be repeated, as no two El Niño phenomena are absolutely identical due to differences in their duration and the overall climate situation on Earth. However, There are already several forecasts regarding what to expect from the upcoming El Niño. Dr. Trasa Castro, a climatology expert, highlights 4 potential consequences for global weather in 2023-2024. First, there is a possibility of even brain disorders and miscarriages due to abnormal heat. Additionally, the Amazon rainforests, as well as forests in Africa, India, and Australia, could face prolonged droughts, leading to reduced vegetation growth and consequently less carbon dioxide absorption from the atmosphere. Fourth, Northern Europe may experience cold and dry winter months, while Southern Europe, on the contrary, may face increased precipitation. In particular, the North Atlantic may experience a cooling period during El Niño. Access to food resources and drinking water is becoming an increasingly acute problem, so it is likely that this time will be no exception. Australia, Brazil, Peru, Africa, and other countries and continents that endured dramatic climate changes in 2015 and 2016, unfortunately, may again face a serious food and economic crisis. It is also possible that the export of many agricultural and livestock products, as well as mining products and fuel, will sharply decrease, which will indirectly affect the entire world. The National Oceanic and Atmospheric Administration, NOAA, also predicts that the United States may face a significant increase in precipitation in the eastern regions of the country, as well as intense heat in the southwest and south. In particular, these 2 weather phenomena are capable of disrupting the formation processes of tropical forests in the future. Nevertheless, one of the key factors contributing to the strengthening of El Niño and La Niña's influence is the emission of greenhouse gases, which further heat our planet. We can expect constantly high global temperatures to become the norm and continue to rise, posing an even greater threat to the entire world. The possible future deterioration of the planet's weather situation is an alarming signal for each of us, as only careful stewardship of the environment can protect humanity from catastrophic consequences. In the vast expanse of our solar system lies a great mystery, an inexhaustible source of energy and life, our Sun. For 10 years, a cosmic guardian known as NASA's Solar Dynamics Observatory, or SDO, has been our vigilant eye, continuously observing this fiery giant. This mission, launched into space on February 11, 2010, embarked on an odyssey not only to observe, but also to deeply comprehend the mysteries of our closest star. Imagine a world where every fraction of a second reveals a story millions of years old, where fiery plumes, larger than Earth itself, erupt from the Sun's surface. This is the world SDO explores, a world where a new image is created every 0.75 seconds, each an integral piece of a complex puzzle in understanding the Sun's overarching influence on our solar system. As we delve into a decade of continuous solar observations, we find ourselves in a realm where colossal waves ripple across the Sun's surface, where plasma eruptions challenge our current understanding of the laws of physics, and where the solar cycle resonates throughout the solar system. This is not merely a story of a satellite and a star. It is a narrative of grand discoveries, of encounters with numerous challenges, and their successful overcoming. Our journey with the Solar Dynamics Observatory begins with an epical event, the launch on February 11, 2010. To the thunderous roar of engines and the blazing ascent of an Atlas V rocket, SDO began its mission to deeply explore the Sun's mysteries. This launch marked not only the beginning of the mission itself, but also the dawn of a new era in solar observations. Once in space, SDO entered a geostationary orbit, positioned to provide an unobstructed and constant view of the Sun. Its primary goal is to understand the Sun's influence on Earth and the entire solar system by studying the solar atmosphere in unprecedented precision and detail. Central to this mission is a sophisticated suite of instruments aboard SDO, each designed to study different aspects of the Sun's behavior. Among them, the Atmospheric Imaging Assembly, or AIA, stands out. This remarkable instrument captures images of the solar atmosphere at various wavelengths, each revealing unique features of the Sun. AIA's capabilities are truly revolutionary. It observes the Sun in 10 different wavelengths, each tuned to a specific temperature of solar material. This allows scientists to see the Sun's surface and atmosphere in a wide spectrum of colors, with each color revealing unique physical phenomena. AIA's observations have played a key role in significantly advancing our understanding of solar dynamics, from studying cooler, darker sunspots to analyzing blazing hot coronal loops. Over the past decade, it has tirelessly observed the Sun, capturing over 425 million high-resolution images. Each image contributes to a continuous stream of data, painting a vivid and dynamic portrait of the Sun's behavior. Why does humanity study our star so diligently? The answer lies in the Sun's profound impact on our entire system. It is the pulsating heart of our cosmic abode, regulating processes ranging from the mesmerizing auroras on Earth to the meteorological conditions on other planets. Comprehending the Sun is equivalent to comprehending the fundamental mechanisms governing our corner of the vast universe. Through the eyes of the AIA, or Atmospheric Imaging Assembly, we have watched the Sun's history unfold in real time, like a cinematic reel. Eruptions of solar material, intricately twisting magnetic fields, and the intricate dance of flares, all have been captured in stunning detail. AIA didn't just open a window into solar activity, it paved the way for a profound understanding of the complex interconnections that define space weather. This decade of observation has revealed the dynamic nature of the Sun with unprecedented thoroughness, from the ebb and flow of solar flares to the enigmatic 11-year solar cycle. The Solar Dynamics Observatory has provided invaluable insights into phenomena that were once merely subjects of conjecture. The mission has witnessed previously unfathomable solar events, pushing the boundaries of our knowledge. In the vast expanse of space, the Solar Dynamics Observatory, or SDO, acts as a vigilant observer, capturing every subtlety of the Sun's behavior with unprecedented precision. Over its decade of fruitful work, SDO has amassed a stunning collection of over 425 million high-resolution images, creating a continuous and detailed portrait of the Sun's ever-changing face. Imagine a world where every fraction of a second reveals a new, previously unknown aspect of our star. SDO operates in precisely this mode, capturing images of the Sun every 0.75 seconds. This relentless pace of observation allows us to see the dynamic nature of the Sun in real time, capturing processes and changes that were once beyond our sight and understanding. The Solar Dynamics Observatory's ability to observe the Sun at various wavelengths has opened up exciting new possibilities for a comprehensive understanding of our star. Each wavelength reveals a unique layer of the solar atmosphere, from its turbulent surface to the outer reaches of its corona. This multi-wavelength approach allows us to see the Sun in all its majestic diversity. Among the many wavelengths that SDO observes, the extreme ultraviolet wavelength of 17.1 nanometers holds a special place. This particular wavelength gives us a unique, unprecedented view of the solar corona, the outermost and most mysterious part of its atmosphere. The corona is a hotbed of solar activity, where temperatures reach millions of degrees, and where the secrets of grand solar phenomena such as coronal mass ejections and solar flares are hidden. Through the lens of the Solar Dynamics Observatory, the corona is no longer a dark and unexplored region, but appears as a vibrant, dynamic environment. We see coronal loops, giant arcs of plasma driven by the Sun's powerful magnetic field, and observe eruptions that send waves of solar material deep into space. These observations are not just visually stunning, they are key to understanding how the Sun influences space weather and, in turn, our own planet. As we continue to explore the Sun with SDO, each image and observation at every wavelength adds to our understanding of our star's enigmatic corona, revealing a dynamic and complex celestial body like never before. Taking on the ambitious task of deciphering the 11-year solar cycle, the Solar Dynamics Observatory has been at the forefront of solar science. This cycle, whose rhythm has puzzled astronomers for years, is characterized by periodic changes in the sun's activity, including the frequency of sunspots, solar flares, and coronal mass ejections. SDO's decade-long observations span almost a complete solar cycle, offering a front-row seat to the sun's changing dynamics, like a grand cosmic spectacle. During periods of solar maximum, the sun is a hive of activity, teeming with sunspots and erupting with intense solar flares, like a giant cosmic fireworks display. Conversely, during solar minimum, the sun enters a quieter phase with fewer sunspots and significantly less surface activity, like a sleeping giant. Throughout its mission, SDO has witnessed and meticulously recorded many solar events. Incredible eruptions of plasma, known as coronal mass ejections, have been captured in minute detail, revealing the immense energy released as these grand events unfold. Solar flares and intense bursts of radiation have been observed across various wavelength ranges, providing invaluable information about the mechanisms that trigger these explosive phenomena. In addition to this magnificent spectacle, the SDO spacecraft also had the opportunity to observe rare and truly mesmerizing planetary transits across the sun's disk. These phenomena, which are captivating astronomical events in themselves, serve an even more important purpose in solar science. They provide scientists with unique opportunities for detailed study of the sun's atmosphere and its complex interactions with various celestial bodies, which, in turn, significantly expands our comprehensive understanding of the dynamic processes occurring on the sun. In the vast and complex endeavor of space exploration, challenges and difficulties are as inevitable as they are diverse. NASA's Solar Dynamics Observatory, SDO, has also encountered its share of serious obstacles on its journey, each a test of the mission's strength, resilience, and ingenuity. From periodic shadows cast by Earth and lunar eclipses to complex technical malfunctions, such as the AIA instrument issue in 2016, SDO's path has been marked by many thorny stretches and winding turns. One of the constant and unavoidable challenges that SDO regularly faces are eclipses caused by the passage of Earth and the Moon. These celestial landmarks, while a natural and predictable part of the spacecraft's orbital path, temporarily but significantly limit SDO's ability to continuously observe the sun. Earth eclipses, which occur during equinoxes, cast a vast shadow on the Space Observatory, leading to brief periods of complete darkness and inevitable interruptions in the transmission of valuable scientific data. Similarly, lunar transits across the sun's disk, while much rarer events, momentarily completely block SDO's view of the sun, creating a unique but very challenging scenario for conducting comprehensive solar observations. In 2016, the SDO mission faced a particularly serious challenge when its key scientific instrument, AIA, experienced significant technical difficulties. This unforeseen malfunction jeopardized one of the most important data streams coming from the mission. The AIA instrument, responsible for high-resolution imaging of the solar atmosphere at various wavelengths, is an absolutely integral part of deeply understanding the sun's dynamic and often unpredictable behavior. The problem that arose with AIA was extremely complex and concerned difficulties in detecting and subsequently analyzing so-called invisible coronal mass ejections, or CMEs. These CMEs, which occur at significant altitudes in the solar corona and in areas with extremely weak magnetic fields, are inherently extremely difficult to observe using standard methods. Unlike typical coronal mass ejections, which usually appear as visible darkenings on the solar disk, these particular CMEs were termed invisible. To solve this complex problem, a team of scientists and engineers applied completely new and innovative methods for visualizing remote sensing data obtained using the AIA instrument. By carefully comparing current images of the Sun with images taken 12 hours earlier, the team was able to successfully capture slow but important changes occurring in the lower layers of the solar corona. This advanced method allowed for the detection of subtle, previously completely unnoticed changes in the Sun's magnetic fields and in the structure of plasma loops. To further improve the visibility of these extremely subtle changes, even more advanced image processing methods were applied, including complex algorithms such as wavelet packet alignment and multi-scale Gaussian normalization. These modern data processing techniques allowed the team to detect darkenings that were too faint to be noticed by conventional means, significantly expanding the observational capabilities of SDO as a long-term space observatory designed for continuous study of the Sun. As we delve deeper into understanding the implications of the scientific discoveries made by the Solar Dynamics Observatory, we inevitably uncover the profound and pervasive influence of the Sun, not only on our planet Earth, but also on the much broader expanses of outer space. Decades of continuous and meticulous observations conducted by SDO have significantly advanced our understanding of the phenomenon of space weather and its numerous, often critically important consequences for our planet and for our entire technological civilization, extending far beyond its borders. Space weather is an overarching term used to denote the energetic activity of the Sun, which includes diverse and powerful phenomena such as solar flares, coronal mass ejections, and streams of solar energetic particles. These grand events, born on the dynamic surface and in the vast atmosphere of the Sun, can propagate through interplanetary space, significantly impacting both the planets of the solar system and numerous spacecraft in orbit. As for Earth, the consequences of space weather are both fascinating and far-reaching. The interaction of powerful solar wind and gigantic coronal mass ejections with Earth's magnetosphere can lead to the emergence of spectacular auroras, widely known as the northern and southern lights. However, these interactions can also have much more destructive consequences, such as serious disruptions to satellites, communication systems, and even global power grids, which underscores the importance of studying them. The scientific discoveries made by the SDO mission have played an extremely significant role in substantially enhancing our ability to accurately predict space weather events. Thanks to a deeper understanding of the complex mechanisms that cause solar eruptions and their projected trajectories, scientists can now much better predict when and how these events may affect Earth. Such accurate forecasting is crucial for timely preparation and reliable protection of our vital technological infrastructure, both in space and directly on Earth. Beyond Earth, the impact of research conducted by the SDO mission extends throughout the solar system. Understanding the dynamics of space weather is paramount for ensuring the safety of space travelers, as well as for the meticulous planning and successful execution of interplanetary expeditions. As humanity continues its aspirations into the depths of space, be it to the Moon, Mars, or beyond, knowledge of our star's behavior becomes increasingly critical. Thus, the consequences of the decade-long period of observations conducted by the SDO spacecraft are profound and have far-reaching prospects. This mission has not only significantly expanded our understanding of space weather and its impact on Earth, but has also laid a solid foundation for ensuring safer space exploration for many decades to come. As we turn our gaze to the future of solar observations, the horizon appears full of hope and untapped potential. The modern era of solar study is marked by the advent of groundbreaking missions such as the Parker Solar Probe and the Solar Orbiter. The Parker Solar Probe, launched in 2018, has already approached the Sun closer than any other spacecraft before it, and will ultimately plunge into the corona to unlock its innermost secrets. The Solar Orbiter, a result of a fruitful collaboration between the European Space Agency and NASA, launched in 2020, is equipped to provide a comprehensive view of the Sun's poles and its outer atmosphere, regions that have previously remained unexplored. These missions are outfitted with state-of-the-art instruments specifically designed to study the Sun in entirely new ways. The Parker Solar Probe's journey through the solar corona promises to provide invaluable insights into the fundamental processes that govern the solar wind and solar energetic particles. The solar orbiter's unique orbit and extensive suite of instruments will provide a holistic and comprehensive view of the Sun's atmosphere, its magnetic field, and the solar wind. Looking ahead, the future of solar observations holds brilliant potential. The opportunities for new discoveries are as limitless as the Sun itself. We may unlock the innermost secrets of the Sun's magnetic field dynamics, leading to a significantly better understanding of solar flares and coronal mass ejections. Studying the Sun's internal mechanisms may reveal more about the workings of its 11-year solar cycle. As we continue to observe and study the Sun, we stand on the cusp of a new era in solar science, one that promises to illuminate the darkest corners of our understanding of the star that supports life here on Earth. Imagine a world teeming with the raw materials for life, hidden among the stars. What if some of the most promising candidates for alien These worlds may hold the secrets to the origin of life, offering conditions favorable for the formation of organic molecules. Thanks to its unprecedented sensitivity and advanced infrared capabilities, the James Webb Space Telescope has detected diamond-like carbon dust from the earliest stars in the universe. It is this carbon dust that plays a crucial role in the formation of stars and planets. But what makes these exoplanets so intriguing? Carbon is a fundamental element of organic chemistry, the basis of life as we know it. These planets may have all the conditions conducive to the formation of complex organic compounds, potentially leading to the emergence of life. And it is possible that around these miniature stars, where conditions are stable and long-lasting, rocky planets with carbon-rich environments could be ideal laboratories for experimenting with life. Should we reconsider our understanding of where life might exist beyond Earth? A little about the basics. After all, life on a planet cannot exist without the planet itself, right? The birth of planets and the essential ingredients for life contained within them are found in protoplanetary disks, vast rotating structures of gas and dust that surround young stars. These disks are the cradles of planets and the complex chemistry that lays the groundwork for the origin of everything in a planetary system, including the formation of organic molecules. Recent studies, conducted with high-tech astronomical instruments such as the Atacama Large Millimeter Submillimeter Array, ALMA, have confirmed the presence of a vast diversity of organic molecules in these cosmic disks. Compounds such as methane, formaldehyde, and acetylene are formed as a result of complex chemical transformations occurring in the cold and dense regions of protoplanetary disks. The synthesis processes of these vital substances are triggered by collisions between gas and dust particles, as well as by ultraviolet radiation emanating from the central star and cosmic rays. Organic molecules are of colossal importance because they represent the first stages in the origin of life on Earth. Simple organic compounds serve as starting materials for the formation of more complex structures, such as amino acids and nucleotides, which in turn form proteins and deoxyribonucleic acid, or DNA. The presence of these molecules in protoplanetary disks serves as convincing evidence that the basic building blocks of life may be widely distributed throughout the universe, naturally arising during the formation of planetary systems. For an in-depth study of these cosmic processes, scientists have conducted a series of laboratory experiments using the James Webb Space Telescope, or JWST. These studies have significantly expanded our understanding of the chemical composition of these disks. High-resolution infrared observations carried out by the telescope have provided detailed information about the chemical transformations occurring in the early stages of planetary system development. Simultaneously, many key molecules have been identified, including water, carbon dioxide, and complex organic compounds, vividly demonstrating the chemical diversity of the environment. One of the most significant discoveries made by the James Webb Space Telescope is the detailed mapping of the distribution of these molecules in protoplanetary disks. The created map clearly shows how the chemical composition changes with distance from the central star, revealing regions abundant in ice and organic compounds, which are crucial for the planet formation process. The results suggest that young planets incorporate these organic molecules into ice during their formation, which can later contribute to the creation of a life-favorable environment. An in-depth understanding of the chemical composition of protoplanetary disks expands our knowledge of the mechanisms of planet formation and evolution. The presence of organic molecules and other complex compounds provides the necessary ingredients for the origin of life, and suggests that the potential for its emergence is inherent in the very essence of the planet formation process. As these molecules are incorporated into developing planets, they can be preserved in comets and asteroids, which can later deliver them to planetary surfaces through cosmic collisions. The chemical processes occurring in the disks also indicate dynamic interactions between forming planets and their environment. For example, the movement and mixing of materials within the disk can lead to the formation of various planetary compositions and atmospheres. This chemical diversity is crucial for creating different planetary environments, some of which may also be favorable for the development of life. One of the most remarkable discoveries by the James Webb Space Telescope last year was the detection of diamond-like carbon dust originating from some of the earliest stars in the universe. This extraordinary finding provides new insights into the processes that shaped the early cosmos. JWST's infrared sensors are capable of capturing the faintest signals emanating from distant celestial objects. By analyzing the spectra of light emitted by ancient stars, scientists have identified signs of diamond-like carbon dust. This form of carbon is characterized by a crystalline structure, somewhat resembling Earth's diamonds. Carbon dust plays a critically important role in the formation of stars and planets. In the early stages of star formation, carbon dust acts as a cooling agent, contributing to the compression and collapse of gas within a molecular cloud under the influence of gravity. This cooling is necessary for the cloud to shrink and form new stars. As stars evolve and complete their life cycles, they eject carbon-rich materials into space, seeding the interstellar medium with the ingredients necessary for the next generation of stars and planets. In addition to its cooling function, carbon dust actively contributes to the formation of solid cosmic bodies in protoplanetary disks. These disks, which are accumulations of gas and dust surrounding young stars, are essentially the cradles where planets are born. Carbon dust in such disks has the ability to clump together and gradually increase in size, thereby forming the building blocks from which rocky planets are subsequently formed. The presence of diamond-like carbon dust suggests that even in the earliest planetary systems, all the necessary components for the subsequent formation of planets could have existed. The implications of this momentous discovery extend far beyond our current understanding of the early universe. The detection of diamond-like carbon dust in young stars indicates that carbon was abundant even in the earliest stages of the universe's development. This conclusion suggests that conditions favorable for the formation of carbon-containing molecules and, possibly, for the origin of life, existed significantly earlier than previously assumed. Moreover, the presence of carbon dust in the early universe helps astronomers build a more accurate chronology of cosmic evolution. It indicates that the first stars, known as population 3 stars, which formed shortly after the Big Bang, played a key role in enriching the universe with heavy elements such as carbon. As these massive stars went through their life cycles and ended in death, they ejected their carbon-rich material into space, thereby contributing to the increased chemical complexity of the cosmos. Overall, a carbon-rich environment is absolutely necessary for the development of complex carbon-based life forms. While other elements and compounds undoubtedly play important roles, it is carbon's unique properties that make it indispensable for the development of life. And it is indispensable, of course, due to its unique ability to form stable, complex molecules. It can bond simultaneously with 4 other atoms, thereby creating a huge number of organic compounds that are critically important for all biological processes. This amazing versatility allows carbon to form long chains and rings, which serve as the basis for proteins and other vital molecules, providing the degree of complexity necessary for the full functioning of organisms. Even more intriguing and truly revolutionary is another discovery made with the James Webb Space Telescope this June. A team of over 40 scientists from all corners of the world was able to peer into the protoplanetary disk surrounding small stars. The study of ISO-CHA I-147, a young star located in the Chameleon 1 star-forming region, revealed the richest set of hydrocarbons ever observed in a planet-forming disk. Among them is the first detection of ethane outside our solar system. The discovery of ethane is revolutionary because it is a key hydrocarbon that plays a significant role in the chemistry of life. Ethane is a simple molecule that can serve as a precursor for the formation of more complex organic compounds. These results suggest that protoplanetary disks surrounding tiny stars are particularly effective at forming small Earth-like planets, rather than large gas giants like Jupiter. This is extremely important because low-mass stars are more common in the Milky Way, indicating that there may be many more Earth-type planets in our galaxy than previously thought. The protoplanetary disk surrounding this star is characterized by a carbon-rich chemical composition with 13. This chemical composition differs significantly from disks surrounding Sun-like stars, where oxygen-containing molecules predominate. The presence of these hydrocarbons in such significant quantities suggests that material is transported radially along the disk, influencing the fundamental composition of the planets that form within it. These differences in chemical composition mean that rocky planets forming around tiny stars may have different atmospheres than Earth. For example, the primary atmospheres of many of these planets may be dominated by hydrocarbon compounds, rather than oxygen-rich gases. This could lead to the formation of carbon-rich planets with atmospheres completely unlike our own. The discovery of such carbon-rich cosmic environments represents a cornerstone for a deep understanding of the potential origin of Earth-like life. Carbon, as is known, serves as the fundamental basis of organic chemistry, being an integral part of DNA, proteins, and many other vital biological molecules. The presence of such molecular structures in protoplanetary disks suggests that the building blocks for the emergence of life may be widely distributed throughout the vast universe, forming naturally in the process of planet creation. Moreover, these striking discoveries vividly highlight the dynamic and constantly changing nature of protoplanetary disks, as well as the extremely complex processes that ultimately lead to the formation of planetary systems. The imbalance between carbon and oxygen content in these disks is likely the result of so-called enrichment processes, during which solid particles lose their carbon content, releasing it in a gaseous state. Such carbon-depleted particles then form planets with a rocky, carbon-poor core, but their atmospheres turn out to be dominant in carbon content. The distinction between carbon-enriched disks and oxygen-enriched disks is paramount for understanding the potential for life to arise on the planets forming there. Carbon-rich disks, dominated by hydrocarbons such as ethane, could potentially foster the development of life forms based on entirely different biochemical processes than those known to us on Earth. In contrast, oxygen-rich disks containing molecules such as water and carbon dioxide are much more similar to the conditions believed to have led to the emergence of life on our own planet. This vast chemical diversity implies that planets forming in such differing environments may possess significantly varied atmospheres and surface conditions. Potentially, this could lead to the emergence of the widest range of life forms or prebiotic chemistry that we are not yet able to even imagine at this stage of scientific development. The discovery of rocky, carbon-rich exoplanets orbiting small stars not only expands our understanding of the incredible diversity of planetary systems, but also instills new hope for the detection of life beyond Earth. Small stars, around which such carbon-rich exoplanets may orbit, are extremely common in our galaxy. They often differ in greater stability compared to larger stars and are capable of providing a constant and stable habitat for billions of years. This stability significantly increases the likelihood that life will have enough time to fully develop and evolve. However, carbon is not the only key element necessary for the origin and maintenance of life. What else is needed for its existence? In the context of the search for life beyond our solar system, the concept of the habitable zone, often called the Goldilocks zone, acquires critical importance. These zones are regions around a star where temperature conditions are optimal for the existence of liquid water on a planet's surface. Liquid water is extremely important because it is a key. The size and location of habitable zones directly depend on the type and size of the star. For smaller, cooler stars, the habitable zone is located closer to the star, while for larger, hotter stars, it is located significantly farther away. The search for planets located in these zones is one of the key tasks for astronomers, striving to discover potentially habitable worlds. One of the most modern and high-precision instruments helping in this search is the Habitable Zone Planet Finder, or HPF for short. This instrument, installed on the Hobby Eberly telescope in Texas, is designed specifically to detect exoplanets orbiting low-mass stars. It does this by measuring tiny changes in starlight that are caused by the gravitational pull of planets orbiting them. HPF is particularly effective at finding planets in the habitable zones of these stars, which are often dimmer and cooler than our Sun. Using HPF, astronomers have made significant progress in detecting planets where life could potentially exist. By focusing on low-mass stars, which are the most common in our galaxy, the instrument significantly increases the chances of finding habitable planets. HPF's high precision allows scientists to detect even small, Earth-sized planets that might otherwise go unnoticed. In this context, a highly unexpected and intriguing discovery has emerged, challenging all existing models of solar system formation and shedding entirely new light on the incredible diversity of planetary systems in the universe. The identification of LHS 3154b, an exoplanet that is astonishingly massive for its relatively small host star, suggests that mechanisms are at play in planet formation processes that we do not yet fully understand. Traditional concepts of planet formation, such as core accretion and disk instability, typically postulate that a star's mass sets a limit on the sizes of planets that can arise around it. However, exoplanet LHS 3154b completely contradicts this established rule. It is possible that this planet formed at a significant distance from its star and then gradually migrated closer to it, or it could have been captured from an entirely different star system. Such scenarios shed entirely new light on the dynamic processes of planetary system formation and subsequent evolution. It is particularly noteworthy that this exoplanet still maintains conditions potentially capable of supporting liquid water. The presence of such a planet indicates that habitable zones can exist in a much wider range of conditions than previously assumed. However, the presence of such a massive planet in the habitable zone of a small star also has significant implications for the potential habitability of other planets in the same system. Its powerful gravitational influence can both create and completely destroy a habitable zone, impacting the climatic conditions and geological processes of all smaller, potentially habitable planets nearby. This can either stabilize conditions favorable for life, or conversely, make them significantly more unstable, depending on the specific characteristics of the system. Interestingly, the unexpected size of this planet suggests insights into the evolutionary paths of planets. It may well represent a certain stage of planetary evolution that humanity does not yet fully comprehend. For example, some gas giants can lose their atmospheres due to intense stellar radiation or as a result of gravitational interactions, leading to a significant decrease in their size and mass. This process is known as planetary evaporation or contraction. In the context of LHS 3154b, its impressive mass and very unusual orbit suggest that it may be undergoing or has already undergone similar evolutionary processes. The planet could have initially formed as an even larger gas giant, subsequently losing part of its gaseous envelope. Or it could have originated in another part of the star system and then migrated under the influence of the host star's dynamic environment. Such discoveries strongly challenge the notion that only Earth-like planets orbiting Sun-like stars can be habitable, and suggest that life can exist in the most diverse and unexpected environments. As humanity continues to actively explore outer space, the quest to discover and comprehensively understand exoplanets remains a central focus of astronomical research. Current and future space missions are poised to revolutionize our knowledge of these distant worlds, especially those located in habitable zones. One of the key participants in this ongoing exploration is the Transiting Exoplanet Survey Satellite, known as TESS, launched in 2018. TESS is specifically designed to observe the brightest stars located near Earth, searching for transiting exoplanets. Its primary mission is to identify thousands of new exoplanets, whose sizes range from Earth-sized to gas giants, and to provide targets for further study by other telescopes. TESS has already discovered numerous planets, some of which are located in habitable zones, making them prime candidates for detailed study. The European Space Agency's Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey mission, scheduled for launch in 2029, is expected to study the atmospheres of 1,000 exoplanets. By analyzing the chemical composition and thermal properties of these atmospheres, Ariel will help scientists gain a deeper understanding of the formation and evolution processes of planetary systems, as well as the potential habitability of these distant worlds. Furthermore, proposed future missions such as LUVOIR and HABEX have the potential to take exoplanet research to an entirely new level. The goal of these missions is to directly image exoplanets that are particularly similar to Earth and to search for signs of habitability, including even potential biosignatures. By studying the light reflected from these planets, scientists hope to detect biomarkers such as oxygen and methane in their atmospheres. Many exciting events loom on the horizon, and they promise to significantly expand our knowledge and inspire further curiosity about the boundless cosmos. As we learn more about these distant worlds, the enduring question remains: are we alone in this vast universe, or is life simply waiting to be discovered? By now, humanity has fully embraced the idea that the origins of life lie in the boundless expanse of the ocean. Nevertheless, a number of pressing questions continue to provoke fierce debates in academic circles. For example, how did living organisms transition from aquatic environments to land? What would be the potential benefit of a massive meteorite impact for the development of life? How critical is a collision with another celestial body for the origin and evolution of life? What did our planet look like during its first few million years of existence? And what colossal challenges did it face? Some of these questions have already found answers, and these solutions will be discussed further. The hypothesis that life originated in water and then successfully migrated to land seems very plausible. After all, oceans currently cover more than 70% of Earth's surface and are home to an innumerable multitude of diverse organisms, some of which are so superficially studied that scientists are still discovering new species. Once on land, these unique life forms successfully adapted to new conditions and evolved to ultimately give rise to Homo sapiens. Everyone remembers Charles Darwin's famous theory that fish once decided to vacation on land. Modern scientists have provided comprehensive explanations for this theory. An interesting fact: regardless of how many refutations of Darwin's theory one can read, representatives of the scientific community just as often accept this theory as a fundamental starting point for further research. The main question facing researchers is, what else besides the ocean is necessary for life to arise? To answer this complex question, one must take a journey into the distant past of the solar system. The process of solar system formation is very similar to what happened in our neighboring star systems. At a certain point, approximately 13.6 billion years ago, a colossal Big Bang occurred. According to scientists, this event caused the creation of the universe as we observe it through telescopes. The consequences of this grand event led to the formation of the first chemical elements, hydrogen, which, compressing and heating under the pressure of the explosion's energy, transformed into a new element, helium. This accumulation of compressed hydrogen turning into helium is called a protostar. However, protostars did not remain in their pristine state for long. The main benefit of their existence was the emergence of new chemical elements, which subsequently became the fundamental building blocks for the origin of life. First and foremost, this led to the emergence of ordinary stars. Each star has a unique life cycle during which it is like a grand factory. Something continuously burns, smoke is emitted, and streams of resources circulate to produce something new. Simultaneously, all these processes have a significant impact on ecology and the environment. Similarly, our Sun, like any other star, performs the same functions but on a truly cosmic scale. And then the life of a stellar factory turns out to be quite prosaic. It either expands into a supernova or turns into a red giant or a dark dwarf, which is inevitably followed by extinction and death. Alternatively, a star can transform into a black hole. We know with certainty that the Sun will eventually become a red giant, expand, and engulf nearby planets, including ours. However, we still have approximately 5.5 billion years until this event, so humanity will have enough time to watch all its favorite TV shows. What is so special about our solar system? Scientists have hypothesized that the Sun was created as a result of a supernova collapse that occurred near the future solar system. Thus, our star, having arisen from compressed clouds of gas, eventually absorbed such a colossal amount of matter due to gravity that it was enough not only for its own existence but also for the formation of the entire solar system. Everything that did not become part of the newly formed star began to rotate around it, flattening and taking the form of a disk. This was a huge amount of matter, some particles of which would be lucky enough to become a planet, and some would leave the Sun's closest orbit to become a comet or a dwarf planet. The future cradle of humanity arose somewhere in this cosmic dance. In its early existence, Earth was something resembling a stew of molten lava rock and incredible mixtures of gases released during melting. Near Earth's surface, temperatures exceeded 1,200 degrees Celsius. There was no atmosphere in the usual sense, only carbon dioxide, nitrogen, and water vapor. Moreover, the planet was continuously bombarded by comets and meteorites, some attracted by the planet itself and some by the Sun. Hence the water particles that eventually reached Earth. But at this stage, there was, of course, no talk of life. Our planet experienced the most grandiose impact in its history, which, as it turned out later, was also the most beneficial. A Mars-sized planet, later named Theia by scientists, crashed into Earth. The result of this colossal collision was the formation of Earth's modern shape and size, but even more importantly, the detached fragments gave birth to our natural satellite, the Moon. Initially, it was located significantly closer to us, at a distance of only 13,600 miles. This circumstance subsequently played a significant role. The importance of the Moon would become more obvious as Earth cooled. Over time, Earth's temperature began to gradually decrease, leading to the formation of the Earth's crust and a dense layer of air. Everything our planet gathered through gravity during its formation, after cooling, left only the very core, molten iron, hot and liquid. It is the internal activity of this core that generates the magnetic field around Earth and ensures its stable movement both around its axis and in orbit around the Sun. As the temperature continued to drop, approximately 3.8 billion years ago, the planet experienced its first rains. It was subjected to a powerful meteorite shower. Remnants from the formation of the solar system continuously bombarded Earth. However, inside these bombs was also something extremely useful, namely, Water. These were not yet the rains we are used to. At that time, Earth's rotation speed was so high that a day lasted only 6 hours. Nevertheless, thanks to this extremely useful rain, the first ocean formed on Earth. Meteorite rains continued for 20 million years, so the low water content in each individual meteorite was not a problem. Quantity eventually turned into quality. At this stage of Earth's development, scientists faced an important question. Where did the water actually come from? There are two main theories on this matter. Some researchers believe that all the water was delivered to our planet by meteorites. The second theory suggests that water was already present on Earth from the beginning. The dispute was resolved over time and thanks to new discoveries. Both theories turned out to be simultaneously partially correct and partially incorrect. The study of soil samples from the Moon's surface showed that the then young and active Sun burned off everything that could evaporate from the planets, including water and gases. That is why scientists still cannot definitively determine whether there is more meteoritic or terrestrial water on Earth. And most likely, they will never be able to give an exhaustive answer to this question. But the main thing is that the collision of Earth and Theia became a catalyst that launched the process of the planet's cooling and the subsequent formation of Earth's atmosphere, which was to serve as protection from solar radiation. The existence of the atmosphere turned into a reliable shield, maintaining all the necessary conditions for the origin of life and not allowing anything harmful to pass through. How did the atmosphere form? Earth cooled, but volcanoes were still active. Due to this volcanic activity, water evaporated, turning into clouds, which then condensed into rain. For millions of years, rains continuously fell on Earth's surface, collecting in lakes, then in seas, and finally in oceans. And this global ocean was extremely turbulent. We know how the Moon affects tides. At that time, the Moon was significantly closer, and its rotation around Earth caused such powerful ocean storms that we could hardly imagine their scale. Some waves reached a height of at least 1,000 feet. Meanwhile, winds on Earth were almost as fast as the speed of sound. So, the ocean rages, the storm is at its peak. Where is life? Modern theories generally agree on one thing. Earth's oceans at that time were an ideal place for life to emerge. However, there were several problems. The main question was, how did organic matter, that is, the chemical elements that are the building blocks of life, arise in these conditions? Let's figure it out. The water and atmosphere of Earth at that time, particularly nitrogen, hydrogen, and carbon dioxide, are elements from the inanimate part of chemical elements, so-called inorganic chemical elements. To answer this question, let's turn to the theory developed by Oparin, an academician from the USSR in 1924, as well as a similar theory put forward by a biochemist from Great Britain named Haldane in 1938. Essentially, these theories are simple. The ocean at that time was constantly replenished with organic substances from the atmosphere, which was continuously subjected to lightning strikes thanks to the endless storm of that period. It was under the influence of these electrical charges that the elements in the atmosphere transformed from inanimate inorganic into living organic and fell into the water. Once in the aquatic environment, the particles slowly gathered together and formed a broth of organic matter, which would subsequently develop into living organisms. The behavior of these particles was similar to that of cells. They could grow, divide, and absorb other chemical elements. While organic substances undoubtedly play a role as building blocks for body formation, the very origin of life required a much more complex mechanism. This necessitated the coordinated work of a unique team of workers and a wise foreman to manage the assembly process. In the context of our cells, DNA fulfills the role of such a foreman, a vast library of instructions defining all aspects of life, from reproductive processes to the creation of complex multicellular structures. The task of directly executing these instructions fell to RNA, which acted as the workers. Oper and Haldane's theory explaining the origin of life largely echoes the legend of Frankenstein's monster, where inanimate matter was also brought to life by a bolt of electricity. The key fact we know is that life originated somewhere in the boundless expanses of the ancient ocean, and for the next 300 million years existed exclusively in the form of single-celled organisms. They obviously were not in any particular hurry to develop into a complex form like humans. However, in fairness, conditions on early Earth would not have provided a chance for anything more complex to develop. The single-celled organisms that lived then were prokaryotes. The fundamental difference between them and us is that their organism consisted of a single cell, lacking a protective membrane and, in most cases, a full nucleus. An excellent example of currently existing prokaryotes are bacteria. First, oxygen began to accumulate on our planet in sufficient volumes to form the very atmosphere we inhabit today. And then, over 1 billion years, somewhere between 3.5 billion and 2.5 billion years ago, a new, truly amazing event occurred. Single-celled organisms, even in that literally toxic atmosphere for them, mastered the art of using light energy to convert water, carbon dioxide, and sunlight into their first food, glucose. A byproduct of this innovative process was even more oxygen release. We call this incredible phenomenon photosynthesis. After Earth cooled and the world ocean formed, something truly terrible happened. 2 grand ice ages occurred. The first, known as the Pongola glaciation, stretched for a full 500 million years. The second, the Huronian glaciation, was a bit shorter, but it nearly wiped out all life on our planet. The Huronian glaciation lasted 300 million years. Its cause was the so-called oxygen catastrophe. This event occurred because, thanks to active photosynthesis, single-celled organisms began to release such colossal volumes of oxygen that it led to the mass extinction of all single-celled organisms that existed without oxygen. And thus, aerobic organisms, those life forms that need oxygen to exist, became dominant on the planet. Next, prokaryotes continued their evolutionary path, transforming into eukaryotes, our closest and oldest ancestors in terms of cellular structure. Eukaryotes had the ability to compete, absorb, and destroy their own kind. They used solar energy as their main source of life and were capable of sexual reproduction. Eukaryotes gradually advanced to land, formed by volcanic activity, producing more and more oxygen in the process. In shallow waters, they united to form the prototype of underwater trees, stromatolites. Subsequently, they evolved into red algae, a key feature of which was the ability to reproduce sexually. This skill served as a powerful impetus for further evolution, ultimately leading to the appearance of the next prototype of modern nature, fungi, which began to colonize land. 540 million years ago, the so-called Cambrian explosion occurred, marked by a sharp and unprecedented increase in the number of living organisms. This momentous event contributed to the emergence of future animals, plankton, and microbes. 70 to 80 million years later, another rapid leap in evolution takes place, when most of the species known to us today appear. The first animals to venture onto land were arthropods. Initially, they simply roamed the land in search of more nutritious food than algae and plankton. But then, they never returned to the aquatic environment. According to scientists, one of the most intriguing species that made the transition from an aquatic to a terrestrial lifestyle is the fish Tiktaalik. Its limbs were surprisingly similar to paws, which allowed them to emerge from the water. For 360 million years, plants that had mastered seed reproduction actively spread across land, and insects would soon take to the air. Amphibians, evolving in the four-legged tetrapods, remained on land, learning to reliably hide their eggs from predators and feed on diverse foods. In the future, these animals would branch into several species, giving rise to lizards, birds, anoles, and primates. However, another grand upheaval arose on the path of life's development: the Permian extinction. This catastrophe, one of the largest in the planet's history, led to the complete annihilation of approximately 90% of all aquatic biological species. Nevertheless, a significant portion of terrestrial life forms managed to survive, despite global changes. For the planetary ecosystem to recover even somewhat from this devastating blow, a colossal period of time was required, about 90 million years, during which the biosphere slowly revived to new diversity. This was followed by the era of dinosaurs, whose dominion on Earth was cut short by a catastrophic collision with a large meteorite, causing the Cretaceous-Paleogene extinction. Although this event led to the disappearance of giant reptiles, birds, their direct descendants, as well as approximately 50% of other biological species, managed to survive and continue their development. Thus, after a series of global cataclysms, life definitively and irrevocably established itself on land, demonstrating its incredible resilience and adaptability. Summarizing the reflections on the path of life's development on our planet, a number of key points should be noted. Our planet, Earth, is characterized by a truly unique combination of factors that are not just favorable, but possibly decisive for the emergence and subsequent development of life in its diverse forms. These include the presence of liquid water, a suitable atmosphere, and stable temperature conditions. Despite all scientific achievements, the fundamental question of biogenesis, that is, the appearance of life from non-living matter, still remains without a definitive answer. However, scientists have a number of intriguing and promising clues to unraveling this ancient mystery. In this search, water and the boundless world oceans act as the primary source of potential answers, containing traces of the oldest processes. However, it should not be forgotten that they are not the only repository of such information. Geological data and astrobiological research also contribute. Modern terrestrial oceans, with their striking chemical composition and volume, are truly exceptional. Their existence and unique characteristics are a direct product of billions of years of Earth's planetary evolution, including geological processes and climatic changes. Humanity lives in a truly amazing era, when scientific breakthroughs concerning the understanding of the mechanisms of transformation of non-living elements into living matter, i.e., the processes of abiogenesis, have approached their final resolution as never before. Researchers, observing this progress, involuntarily experience a kind of anticipation, because the great mystery of life, its origin and development, may be solved and become the property of all humanity in the very near future.